Imagine a colossal object 6 miles wide, hurtling through space at 12 miles per second toward Earth. And it's not science fiction. 66 million years ago, such an asteroid slammed into what is now the Yucatan Peninsula, forming the crater Chicxulub and triggering a mass extinction event. Today, our planet continues to be threatened by near-Earth objects. These include asteroids and comets whose orbits bring them into our space neighborhood. NASA and other space agencies have made significant strides in tracking and understanding these potential threats, but the risk remains. Advanced technology is at work to monitor and mitigate these threats. From kinetic strikes to gravity tractors, humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another Chicxulub-sized asteroid was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn planetary defense, the history, science, and future against such impressive threats. So, 66 million years ago, an event occurred on Earth that was so catastrophic that it changed the course of life on the planet. The asteroid, about 6 miles in diameter, slammed into the Yucatan Peninsula in present-day Mexico, forming what we now call the Chicxulub crater. The immediate aftermath was nothing short of apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and threw huge amounts of debris up into the atmosphere. The impact's most significant and long-lasting effect was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for an extended period, a phenomenon often referred to as impact winter. New research has shed light on the critical role of the fine dust particles in this cataclysmic event. A study was purchased in Nature Geoscience in October 2023 and found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played a significant role in abrupt climate change. The researchers collected 66 million-year-old rock samples from North Dakota, located an impressive distance from the impact site, which contained surprising amounts of these fine dust particles. These particles lingered in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness led to a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit in the first year alone. As sunlight was blocked, photosynthesis stopped. Plants unable to produce food began to die out. This collapse of plant life had a cascading effect on the entire food chain. Herbivorous dinosaurs that relied on plants for food faced starvation. Consequently, the carnivorous dinosaurs that preyed on them also died. This chain reaction led to the extinction of about 75% of all species on Earth. Interestingly, the new study highlights the hitherto unnoticed impact of dust compared to soot and sulfur, which were previously thought to be the main culprits for the prolonged cooling period. The findings suggest that while soot and sulfur block sunlight more effectively, the sheer amount and persistence of dust had a profound and lasting effect. The study also provides insight into how some species managed to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study cast doubt on the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand specific mechanisms of death following a Chicxulub strike. So what are near-Earth objects? NEOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small harmless rocks to massive bodies capable of causing a massive catastrophe. Asteroids are the rocky remnants of the early solar system, mostly found in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate from the outer regions of the solar system and are composed of ice, dust, and rocky material. As they approach the sun, they develop luminous comas and tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, such as the Chicxulub impactor, are capable of causing global catastrophes. To mitigate these risks, space agencies such as NASA and the European Space Agency have developed extensive programs to track and detect NEOs. Telescopes around the world are constantly scanning the sky, identifying and cataloging objects that are approaching Earth's orbit. One of the key instruments in this work is the Wide-Field Infrared Survey Explorer, which has been repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized using the Space Telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming increasingly important. In May 2024, an AI-based algorithm known as Tracklet-less heliocentric orbit recovery, or THOR for short, detected more than 27,000 previously unobserved asteroids in archival telescope images. This artificial intelligence tool analyzes huge amounts of data, identifying and tracking objects with remarkable efficiency. It can process up to 1.7 billion points of light in a single telescope image, connecting them into asteroid trajectories. The Vera C. Rubin Observatory, due to begin operation next year, will further enhance our ability to detect NEOs. Equipped with advanced artificial intelligence software such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first few months of operation, doubling the current known population. Nevertheless, no near-Earth object is large enough to destroy the planet itself, but asteroids of 1 mile or more in size can cause global catastrophes. For this reason, NASA has been tasked with detecting and tracking these large NEOs. As of 2021, NASA has detected over 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can still cause significant regional damage. Take, for example, Apophis, named after the Egyptian god of chaos and destruction, is a near-Earth asteroid that's captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot-wide asteroid initially caused concern because of calculations suggesting a possible collision with Earth in 2029. However, further observations have ruled out the possibility, confirming that Apophis will pass our planet safely. On April 13, 2029, Apophis will make an incredibly close approach to Earth within 30,000 miles of our planet. By comparison, this distance is closer than the orbits of a few high-altitude satellites. This close provides a unique opportunity for scientific observations and research. During the flyby, the asteroid will become visible to the naked eye in some regions, appearing as a bright, moving point of light. This rare event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Deep Space Communications Complex in California will play a crucial role in observing Apophis. Using radar, scientists hope to gather detailed information about the asteroid's surface, features, and rotation. In addition, the NEOWISE mission can provide additional observations by focusing on Apophis's surface, roughness, and composition. These data are invaluable as they'll help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will make a close approach to Apophis during its shortest flyby. The mission's goal is to study the asteroid up close, providing detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of Apophis, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the asteroid's internal composition, which will also contribute to our broader understanding of the formation and evolution of the solar system. The close passage of Apophis has also attracted the attention of international space agencies. Teams from all over the world plan to observe and study the asteroid using ground and space telescopes. As part of the NEOLITE project, researchers from the Julius Maximilian University in Würzburg have proposed several concepts for small spacecraft that could accompany Apophis during its flyby. One proposed mission includes a small satellite that would follow Apophis for 2 months, acquiring high-resolution images and measurements. Another concept combines a small satellite with the European Space Agency's planned Ramses mission, which would provide extensive scientific observations. Although the asteroid poses no immediate threat to Earth, its close approach in 2029 presents a great scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies. To protect Earth, scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy. It involves sending a spacecraft that would collide with an asteroid at high speed, altering its trajectory. This method relies on momentum transfer to move an asteroid into a safer orbit. NASA's 2022 mission Double Asteroid Redirection Test, or simply DART, was the first test of this method. The DART target was a small lunar satellite, Dimorphos. It was orbiting a larger asteroid, Didymos. As a result of the collision, Dimorphos' orbit was successfully altered, providing valuable data for future missions. Another proposed method is the gravity tractor. This method uses gravitational pull of a spacecraft to slowly change the trajectory of the asteroid over time. By maintaining a stable position near an asteroid, the spacecraft's gravity can gradually alter the object's trajectory. Although this method is still theoretical and has not yet been tested in space, it is a promising approach for dealing with potential threats identified in advance. In extreme cases, however, nuclear explosions could be used to deflect or destroy an asteroid. In this approach, a nuclear device is detonated at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that moves the asteroid off course. However, this method is controversial because of the potential risk and legal implications of using nuclear weapons in space. To prepare for potential asteroid impacts, international space agencies regularly conduct simulations and drills. These exercises help own detection, tracking, and deflection strategies. Planetary defense is a global issue that requires cooperation and coordination among countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictional asteroid on a collision course with Earth, allowing participants to practice their response strategies. As we continue to develop and refine our planetary defense strategies, international cooperation and technological advances will play a key role in protecting our world from any space-based threats. These cooperative efforts are essential, especially as we learn more about the diverse nature of the objects that threaten us. Asteroids and comets are often viewed as different celestial bodies. Asteroids are like the rocky remnants of the early solar system, mostly from the belt between Mars and Jupiter. Comets, on the other hand, are aliens from the outer reaches of our system, composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these two categories, exhibiting characteristics of both. One such object is QN173, discovered in 2005. This unique celestial body orbits like an asteroid, but it behaves like a comet. Unlike ordinary asteroids, which are inert, QN173 exhibits comet-like activity, ejecting dust and developing a long, thin tail as it approaches the Sun. 2005 QN173 orbits the Sun every 5 years, spending most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it shows increased activity, similar to a comet. This duality makes 2005 QN173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Last Alert System in Hawaii observed an object displaying a comet-like tail. Further observations by the Lowell Observatory and the Zwicky Transient Facility confirmed the activity. The 450,000-mile tail suggests that the object is covered in icy material that sublimates when heated by the Sun. It's this process that turns the ice directly into gas, releasing dust and creating the characteristic tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the core at extremely slow velocities. This presents a mystery to scientists, as such slow velocities would not normally allow dust to escape the asteroid's gravity. One hypothesis is that the rapid rotation of the core may contribute to the dust ejection. In addition to unique objects like 2005 QN173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a comprehensive risk list, cataloging objects with a non-zero probability of colliding with Earth. The list contains detailed information on the size, velocity, and collision probability of each object. It currently contains over 1,600 targets. The list of risks is sorted by the Palermo scale, a logarithmic scale that assesses the risk of collision based on an object's size, speed, and probability of collision. Objects with higher values on the Palermo scale pose a greater potential threat. Statistical analysis of these potentially hazardous asteroids shows that while most NEOs pose minimal risk, there are a few objects that require close observation. For example, the size and velocity of an asteroid have a very significant impact on its probability of impact and potential damage. Large asteroids, usually over 1 kilometer in diameter, are a particular concern because of their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none of them pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can still cause significant regional damage. Events such as the meteor in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Every few years, the seemingly calm Pacific Ocean hides a secret. Beneath its surface, a powerful force is raging, a climactic phenomenon that affects weather conditions around the world. Its name is El Nino. From torrential rains that cause catastrophic flooding in South America to severe droughts that cause wildfires in Australia, El Nino is not just a tropical oddity. It is a global disruptor. But what causes this climate phenomenon? Let's find out. El Nino, which means the boy in Spanish, affects the water in the ocean, heating it by about 32.4 to 32.9 degrees Fahrenheit above the average temperature. It was first recorded in the 16th century. This phenomenon can be observed in all parts of our planet. El Nino can lead to floods, droughts, increased levels of CO2, and global temperature changes. It begins to spread from the east-central Pacific Ocean. Therefore, developing countries bordering the ocean and marine life that is not prepared for abrupt climate change suffer the most from the sharp heating of water. However, El Nino is not the only phenomenon that can affect global weather. In fact, El Nino is just a phase of a single climate phenomenon called the El Nino Southern Oscillation. This cycle can be in two other phases. One of them is La Niña, which is the exact opposite of El Nino. And the other is a neutral state where there's no particular influence of either of them. La Niña, or the girl in Spanish, is a weather phenomenon that causes cooling rather than heating of water. In general, the water temperature during La Niña decreases by as much as 37 to 41 degrees Fahrenheit. The consequences of this phenomenon for many countries around the world, such as the United States and Canada, are severe rainstorms, floods, and stronger hurricane seasons. But the worst part is that these two phenomena are very difficult to predict and therefore to prepare for. They occur every 2 to 7 years, so they're not regular. Moreover, they're not short-term phenomena. El Nino lasts about 9 to 12 months, while La Niña usually lasts 1 to 3 years. El Nino and La Niña do not appear out of nowhere. Their formation is a very unusual process. Under normal conditions in the Pacific Ocean, trade winds move from a high-pressure zone to a low-pressure zone from east to west. These winds direct warm water in the direction of their own movement closer to Asian countries and Australia. Thus, cold water rises in the east on the coast of South America, which also has a positive effect on fish catch due to the saturation of such water with nutrients. This process is called upwelling. Warm water warms the air, which causes it to rise faster into the lower atmosphere and condense, while cooler air returns to the eastern parts, thus supporting the trade winds. However, if this balance is somehow disturbed, then El Nino or La Niña begins. During El Nino, the winds weaken, so the warm water is not affected by the wind movement to a large extent, and upwelling also decreases. Consequently, the water in the Pacific Ocean begins to heat up evenly in normally cold areas. This in turn means that rains are also changing, causing dramatic weather changes in all parts of the world. For example, in the tropics, the chance of flooding increases, and in Western countries, droughts increase. As an example, we can cite the protected area in Hawaii, Pu'awa'a. Under typical conditions, the average rainfall there is about 2.7 inches in January, but under El Nino conditions in 2010, only 0.4 inches fell there. However, over time, one place of ENSO can change to another, such as La Nina. During La Nina, the winds, on the contrary, become stronger, which increases upwelling and reduces the areas of warm water in the ocean. So, for example, the western parts of the United States and northern parts of South America may experience cooling, while areas in the Indian Ocean may experience warming. Consequently, the regions bordering the Pacific Ocean suffer the most from these phenomena. Approximately 30 to 60 million people died due to severe drought and floods in India, China, and Brazil in the 19th century. In the 20th century, 26 cases of El Nino were recorded, which seriously affected the harvest of Western countries, and in addition, the population of various animals, including sea lions. Thus, the main victims of El Nino are such South American countries as Peru and Ecuador. Most of the economy of these countries depends on the export of fish and fertilizers. However, due to El Nino, upwelling decreases, which leads to massive fish kills, and precipitation increases, so crops and fertilizers are washed away and civilian infrastructure is damaged. On the other hand, droughts are looming in eastern regions such as Indonesia and Australia. Because of this, water bodies and crops are beginning to dry up, which negatively impacts the standard of living and health of people and animals, as well as land fertility. African eastern countries such as Kenya or Tanzania, as well as American countries, suffer from frequent rains, while South Central countries like Zambia or Mozambique suffer from drought. The South United States, in particular Texas, also suffers from increased precipitation during El Nino. However, for example, in California, the phenomena brings rain, which has a positive effect on the harvest of crops like lime and avocado. In particular, Canadian winters are becoming milder. Interestingly, El Nino also affects Antarctica. In its western part, it becomes a little warmer, so more snow falls, but due to a decrease in upwelling, shelf glaciers begin to melt. On the other hand, La Nina helps to increase the mass of these glaciers, which helps to maintain the balance. The direct impact of ENSO on European countries is difficult to document. El Nino brings cold and dry winters to the European continent, which can be harmful to the land. For example, in the 18th century, El Nino greatly affected the harvest of European countries, which was also probably one of the reasons for the outbreak of the French Revolution in 1789. Already in the 19th century, this phenomenon caused about 3 severe famines in various Asian and European countries. So El Nino and La Nina are quite dangerous phenomena for our world. The last time El Nino and La Nina were observed was in 2015 and 16, almost 7 years ago. 2016 was the hottest year on record. It was the most severe of all previous El Nino episodes in the last 50 years, which led to hunger for more than 60 million people. In 2015, equatorial waters were warmer than usual for the entire year. The central part of the ocean then warmed up by almost 37.4 degrees Fahrenheit at its peak in November. and the overall warming temperature was 35 degrees Fahrenheit, which is likely to be a record value since 1860. All continents have been affected by El Nino, directly or not. For example, Australia experienced severe droughts, especially in its eastern and northern parts. This resulted in an early start to the fire season on the continent, with a total of 125 fires. The fire severely damaged large areas of nature in Tasmania, including rainforests and swamps that had hardly ever experienced fires before. Moreover, the worst coral bleaching was recorded during this period, a process that causes corals to turn white and become very vulnerable to death. The spring and fall of 2016 in Australia were among the driest on record, so the harvest was significantly affected. In addition, the heat reduced supplies of ore, the most exported commodity. Regions in Asia also suffered from different weather conditions. For example, 85% of the Philippines and Indonesia experienced severe drought. Large-scale fires broke out in Indonesia, which worsened the air quality in neighboring areas, including Singapore, Malaysia, Thailand, and others. The fires also affected the export of palm oil, which led to higher prices for the product and, as a result, for all food that used the oil. In addition, rice production in Vietnam and Thailand has dropped significantly, in particular due to water shortages. India, in turn, has reduced its supplies of rice, sugar, cotton, and corn. The northern regions of China suffered from droughts, while the southern regions were affected by rain and floods. South America has been severely affected by weather-related disasters in all regions. In 2016, Peru experienced severe flooding and landslides, causing about 5,000 people to lose their homes and reducing shrimp production. Moreover, 150,000 people had to be evacuated from flooded areas in Paraguay, Brazil, Argentina, etc. In addition, Argentina experienced one of the largest locust infestations, which severely worsened the state of agriculture in the country. Adding to this, the return of rains in April 2016. In Colombia, famine started due to droughts. About 2.3 million people needed humanitarian aid, according to the UN. In the Caribbean, there was a shortage of drinking water. St. Lucia even declared a state of emergency in the country. The varying impact of El Nino in Brazil led to a sharp rise in coffee and sugar prices around the world. The United States and European countries, on the other hand, hardly felt the direct impact of El Nino. The states of Missouri, Mississippi, and the United Kingdom received more precipitation than average, but this didn't seriously affect their economies. And finally, the African continent also suffered economically from this phenomenon. Food production in South Africa fell by 6 million tons. In some parts of Zimbabwe, 75% of the harvest was lost. 10 million people in Ethiopia needed humanitarian aid, and about 458,000 children were treated for acute malnutrition. In total, 60 million people around the world suffered from hunger. In addition, unfavorable weather events led to disease outbreaks, especially in Africa and South America. Thus, due to floods in several countries of South America, the Zika virus began to spread, and in Africa, outbreaks of cholera and Rift Valley fever in the east of the continent, as well as malaria, were recorded. In particular, animals suffered from the effects of El Nino, such as marine birds or small mammals, which sometimes causes predators to attack farm livestock. The populations of invasive species, such as locust and tree frogs, have also increased, spoiling crops and increasing the spread of dangerous diseases. We should not underestimate the seriousness of the danger brought by El Nino and La Nina. Meteorologists are already recording signs of El Nino, which is very likely to begin in late summer 2023 or very early in 2024. According to the National Oceanic and Atmospheric Administration, researcher Dylan Amaya and World Meteorological Organization Secretary General Petteri Talas, we may set new global temperature records next year. One of the reasons for the sharpness was the very long La Nina period, which has lasted 3 years and only ended in March. So a lot of heat energy has accumulated in the ocean, and therefore, after the cold snap, all this heat will be released, which will strengthen the effects of El Nino. It is still difficult to say whether the 2015-16 scenario will be repeated, as there are no two El Niños alike due to the difference in the periods of this phenomenon and the overall climate situation on Earth. However, there are already several forecasts of what to expect from the upcoming El Nino. A candidate in climate science at Tricasca Castro names 4 possible consequences for global weather in 2023-2024. First, it's possible that the ocean temperature could rise to 35 degrees Fahrenheit. Moreover, during its peak, temperatures may rise even more, as they did in 2015 and 16, but according to this researcher, it's too early to predict how severe this temperature increase will be. Secondly, after a long period of La Nina, Australia has had a lot of rainfall, but this could all change next year. As the overall temperature on the continent has increased by 34.5 degrees Fahrenheit compared to the beginning of the 20th century, a new super hot year could cause early fires. Thirdly, not only could a humanitarian catastrophe recur in South America, but outbreaks of serious diseases like malaria, the Zika virus, or dengue fever, it could reemerge. And even brain disorders and miscarriages due to abnormal heat could spread. In addition, the Amazon rainforest, as well as those in Africa, India, and Australia, may experience severe droughts, which will reduce the growth of vegetation, and as a result, less CO2 would be absorbed from the atmosphere. And fourth, Northern Europe can expect cold, dry winters, while Southern Europe can expect increased precipitation. In particular, the North Atlantic may experience a cold snap. During El Nino, access to food and drinking water becomes more acute, so there will probably be no exception this time. Australia, Brazil, Peru, Africa, etc., all of these countries and continents that had a hard time with the dramatic climate change in 2015 and 16 may, unfortunately, experience a severe food and economic crisis again. It's also possible that exports of many agricultural and livestock products, as well as mining and fuel products, will decline dramatically, with an indirect impact on the entire world. NOAA also suggests that the United States may suffer from a strong increase in precipitation in the eastern part of the country and a strong heat wave in the southwest and south. A study by researchers at Dartmouth University, led by Christopher Callahan, estimates that the effects of this phenomenon will cost the global economy about $3.4 trillion over the next 5 years. Thus, the second half of 2023 and next year could be extremely difficult periods for the entire world. However, El Nino and La Nina will not stop there. There is a possibility that in the future they become more serious, more frequent. In particular, these two weather events may disrupt the formation of tropical forest in the future. However, one of the main drivers of the increasing impact of El Nino and La Nina is a greenhouse gas emission, which further warm the panel. Therefore, we can expect that high global temperatures may become the norm and continue to rise, which will become an even greater threat to the world. The possible future deterioration of the weather situation on the planet is a signal to all of us, because only taking care of the environment can protect us from catastrophic consequences. In the vastness of our system lurks a considerable mystery, a source of energy and life, our sun. For a decade, the Space Guardian, NASA's Solar Dynamics Observatory, has been our unblinking eye on this fiery giant. This mission, launched into space February 11, 2010, set out on an odyssey not just to observe, but to unravel the mysteries of our nearest star. Imagine a world where a single second reveals a story millions of years old, where plumes of fire burst from the surface of the sun, larger than the Earth itself. It's a world that explores SDO, a world where every 3/4 of a second a new image is captured, each one a piece of the puzzle in understanding the sun's impact on our solar system. As we venture through a decade of solar observations, we're immersed in a realm where colossal waves ripple across the sun's surface, where plasma eruptions challenge our understanding of physics, and where the solar cycle resonates throughout the solar system. This is not just a journey of a satellite and a star. It is a story of discovery, the challenges faced, and overcoming them. Our journey with the Solar Dynamics Observatory begins with a momentous event: launch, February 11, 2010. Amidst the roar of the engines and the fiery takeoff of the Atlas V rocket, SDO begins its mission to explore the mysteries of the sun. This launch marked not only the beginning of the mission, but also the beginning of a new era in solar observations. Once in space, SDO moved into geostationary orbit, positioned to have an unobstructed view of the sun. Its main goal? To understand the sun's influence on Earth and the solar system by studying the solar atmosphere in unprecedented detail. Central to this mission is a suite of sophisticated instruments aboard SDO, each designed to study different aspects of the sun's behavior. Prominent among them is the Atmospheric Imaging Assembly. This remarkable instrument takes images of the solar atmosphere at different wavelengths, each revealing different features of the sun. The capabilities of the AIA are truly revolutionary. It observes the sun in 10 different wavelengths, each tuned to a specific temperature of solar material. This allows scientists to see the sun's surface and atmosphere in a spectrum of colors, with each color revealing unique phenomena. AIA's observations have been instrumental in advancing our understanding of solar dynamics, from cooler and darker sunspots to blazing hot coronal loops. Over the past decade, it's tirelessly observed the sun, taking more than 425 million high-resolution images, each image contributing to a continuous stream of data, painting a vivid portrait of the sun's dynamic behavior. Why do we study the sun so diligently? The answer lies in the sun's profound influence on our system. It is the heart of our cosmic environment, controlling processes from polar lights on Earth to weather patterns on other planets. Understanding the sun means understanding the fundamental processes that govern our corner of the universe. Through the eyes of the AIA, we witness the story of the sun unfold in real time. Ejections of solar material, twisting magnetic fields, and the intricate dance of solar flares have all been captured in stunning detail. The AIA didn't just open a window into the sun's activity, it paved the way to understanding the complex interactions that drive solar weather. This decade-long observation has revealed the dynamic nature of the Sun in unprecedented detail. From the ebb and flow of solar flares to the mysterious 11-year solar cycle, SDO has provided insight into phenomena that was once mere speculation. The mission has witnessed previously unfathomable solar events. Across the vast expanse of space, the Solar Dynamics Observatory plays the role of a vigilant observer, capturing every nuance of the Sun with unprecedented precision. Over its decade-long operation, SDO has amassed a stunning collection of more than 425 million high-resolution images, creating a continuous image of the Sun's ever-changing face. Imagine a world in which every fraction of a second reveals a new aspect of our star. SDO operates in such a mode, acquiring images of the Sun every 0.75 seconds. This relentless pace of observation allows us to see the dynamic nature of the Sun in real time, capturing processes and changes that were once beyond our view. SDO's ability to observe the Sun at different wavelengths has opened up new possibilities for understanding our star. Each wavelength reveals a unique layer of the Sun's atmosphere, from its turbulent surface to the outer limits of its corona. This multi-wavelength approach allows us to see the Sun in all its manifestations. Among the wavelengths that SDO observes, one that stands out is the extreme ultraviolet wavelength of 17.1 nanometers. This particular wavelength gives us a unique view of the solar corona, the outermost part of its atmosphere. The corona is a hotbed of solar activity where temperatures reach millions of degrees and where the mysteries of solar phenomena such as coronal mass ejections and solar flares lie. Through the SDO prism, the corona is no longer a dark region, but a bright, dynamic environment. We see coronal loops, giant arcs of plasma driven by the Sun's magnetic field, and witness eruptions that send waves of solar material into space. These observations are not just visually stunning. They are key in helping us understand how the Sun affects space weather and, in turn, our own planet. As we continue to explore the Sun with SDO, every image and observation at every wavelength adds to our understanding of our star's enigmatic corona, revealing a dynamic and complex celestial body like never before. By embarking on a quest to decipher the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, a rhythm that's puzzled astronomers for years, is characterized by periodic changes in the Sun's activity, including the frequency of sunspots, solar flares, and coronal mass ejections. SDO's decade-long observations cover nearly a full solar cycle, offering a front-row view of the Sun's changing dynamics. During periods of solar maximum, the Sun is a swarm of activity, teeming with sunspots and erupting with intense solar flares. Conversely, during solar minimum, the Sun enters a quieter phase with fewer sunspots and less surface activity. Throughout its mission, SDO has witnessed and meticulously recorded many solar events. Incredible eruptions of plasma known as coronal mass ejections have been captured in detail, revealing the enormous energy released as these events unfold. Solar flares and intense bursts of radiation have been observed in different wavelength ranges, providing insight into the mechanisms that trigger these explosive events. In addition to this spectacle, SDO has also observed rare and mesmerizing passages of planets along the Sun's surface. These events, while exciting in their own right, serve a more important purpose in solar science. They offer unique opportunities to study the Sun's atmosphere and its interactions with celestial bodies, further expanding our understanding of solar dynamics. In space exploration, challenges are as inevitable as they are varied. NASA's Solar Dynamics Observatory has faced its fair share of obstacles, each of which has tested the mission's resilience and ingenuity. From Earth shadows and lunar eclipses to technical obstacles, such as the Atmospheric Imaging Assembly instrument problem in 2016, SDO's path has been thorny and winding. One of the persistent problems SDO faces is eclipses caused by the Earth and Moon. These celestial landmarks, although a natural part of the orbital path, temporarily limit SDO's ability to observe the Sun. Earth eclipses occurring on equinoxes cast a shadow over the observatory, resulting in short periods of darkness and interrupted data transmission. Similarly, lunar transits, although rarer, momentarily block SDO's view of the Sun, creating a unique but challenging scenario for solar observing. In 2016, SDO faced a major challenge when its key instrument, the Atmospheric Imaging Assembly, encountered technical difficulties. This failure jeopardized one of the mission's most important data streams. The AIA, responsible for high-resolution imaging of the solar atmosphere, is integral to understanding the Sun's dynamic behavior. The problem with AIA was complex and revolved around the problem of detecting and analyzing invisible coronal mass ejections. These CMEs, which occur at high altitudes in the solar corona and regions with weaker magnetic fields, are notoriously difficult to observe. Unlike typical CMEs, which appear as visible dimmings or brightenings on the Sun, hidden CMEs can often be detected only with special instruments like a chronograph. Solving the AIA problem required a coordinated effort between engineers and scientists. The team applied new techniques to visualize the remote sensing data acquired by the AIA by comparing different images, current images of the Sun with images taken 12 hours earlier. The team was able to capture slow changes in the lower part of the corona. This method revealed subtle, previously overlooked changes in the Sun's magnetic fields and plasma loops. Advanced image processing techniques, including wavelet packet equalization and multi-scale Gaussian normalization, were applied to improve the visibility of these subtle changes. These techniques allowed the team to detect dimmings and brightenings in the Sun's disk associated with hidden CMEs, which was a breakthrough in solar observation. Successfully addressing these changes not only allowed the mission to continue, but also enriched our understanding of what it takes to sustain a long-term space observatory. As we delve deeper into the implications of the Solar Dynamics Observatory findings, we discover the Sun's profound influence not only on Earth, but also on the broader expanse of space. Decades of SDO observations have greatly advanced our understanding of space weather and its many implications for our planet and beyond. Space weather, the term for the energetic activity of the Sun, includes phenomena like solar flares, coronal mass ejections, and solar energetic particles. These events, born from the Sun's dynamic surface and atmosphere, can propagate through space, affecting both planets and spacecraft. When it comes to Earth, the effects of space weather are both interesting and far-reaching. The interaction of solar wind and coronal mass ejections with Earth's magnetosphere can lead to spectacular auroras, commonly known as the northern and southern lights. However, these interactions can also have more devastating consequences, such as disruptions to satellites, communication systems, and even power grids. The SDO findings have played a significant role in enhancing our ability to predict space weather events. By understanding the mechanisms that cause solar eruptions and their trajectories, scientists can better predict when and how these events might affect Earth. Such prediction is critical to preparing and protecting our technological infrastructure in space and on the ground. Beyond Earth, the implications of SDO research extend throughout the solar system. Understanding space weather is vital to the safety of astronauts in space and to the planning and execution of interplanetary missions. As we venture deeper into space, whether the Moon, Mars, or beyond, knowledge of the Sun's behavior becomes increasingly important. To summarize, the implications of a decade of SDO observations are profound and far-reaching. This mission's not only deepened our understanding of space weather and its impact on Earth, but it has laid the groundwork for safer space exploration for coming decades. As we look into the future of solar observations, the horizon is full of hope and potential. The current era of solar exploration is marked by groundbreaking missions such as the Parker Solar Probe and Solar Orbiter. The Parker Solar Probe, launched in 2018, has already come closer to the Sun than any spacecraft ever before and will eventually dive into the corona to tell us about its mysteries. The Solar Orbiter, the product of a collaboration between ESA and NASA, launched in 2020, and it's equipped to provide a comprehensive view of the Sun's poles and its outer atmosphere, previously unexplored regions. These missions are equipped with state-of-the-art instruments designed to study the Sun in new ways. The Parker Solar Probe's journey through the solar corona promises insight into fundamental processes that govern the solar wind and solar energetic particles. The Solar Orbiter's unique orbit and extensive suite of instruments will provide a holistic view of the Sun's atmosphere, magnetic field, and solar wind. Looking ahead, the future of solar observation has brilliant potential. The opportunities for new discoveries are as vast as the Sun itself. We can unlock the secrets of the Sun's magnetic field dynamics, leading to a better understanding of solar flares and coronal mass ejections. Studying the Sun's inner workings could reveal more about the workings of its 11-year solar cycle. As we continue to observe and study the Sun, we stand on the threshold of a new era in solar science that promises to illuminate the darkest corners of our understanding of the star that sustains life here on Earth. Imagine a world teeming with the raw materials for life hidden among the stars. What if some of the most promising candidates for alien life dwell around the smallest and dimmest stars in our galaxy? Recent James Webb Space Telescope discoveries have revealed a hidden treasure: rocky, carbon-rich exoplanets orbiting tiny stars. These worlds may hold the secrets to the origin of life, offering conditions favorable for forming organic molecules. With its unprecedented sensitivity and advanced infrared capabilities, the James Webb Space Telescope has detected diamond-like carbon dust from the earliest stars in the universe. It is this carbon dust that plays a crucial role in the formation of stars and planets. But what makes these exoplanets so intriguing? Carbon is a fundamental element of organic chemistry, the basis of life as we know it. These planets may have all the conditions conducive to the formation of complex organic compounds, potentially lending to the emergence of life. And it's possible that around these miniature stars, where conditions are stable and long-lived, rocky planets with carbon-rich environments could be ideal laboratories for experiments with life. Should we reconsider our idea of where life might exist beyond Earth? A little bit about the basics. After all, life on a planet can't exist without the planet itself, right?
The beginnings of planets and the essential ingredients for life they carry are found in protoplanetary disks, the huge rotating structures of gas and dust that surround young stars. These disks are the birthplaces of planets and the cradles of the complex chemistry that lays the foundation for the origin of everything in a planetary system, including the formation of organic molecules. Recent observations with powerful instruments like the Atacama Large Millimeter Array have revealed the presence of a rich diversity of organic molecules in these disks. These molecules, such as methane, formaldehyde, and acetylene, are formed by complex chemical reactions in the cold, dense regions of the disk. Collisions between gas and dust particles, combined with exposure to ultraviolet radiation from the central star and cosmic rays, trigger the synthesis of these crucial compounds. Organic molecules are extremely important because they represent the initial steps in the evolution of life. On Earth, simple organic compounds serve as precursors to more complex molecules such as amino acids and nucleotides, which eventually form proteins and DNA. The presence of these molecules in protoplanetary disks indicates that the building blocks of life may be widespread in the universe, forming naturally during the formation of planets. To better understand these processes, the scientists conducted laboratory experiments. With JWST, they've greatly expanded our understanding of the chemical composition of these disks. Its high-resolution infrared observations have provided detailed insights into the chemical processes occurring in the early stages of planetary systems. At the same time, a variety of key molecules, including water, carbon dioxide, and complex organic compounds, were detected, demonstrating the diversity of the chemical environment. One particular discovery made by JWST is the detailed mapping of the distribution of these molecules in the disks. This map shows how the chemical composition varies with distance from the central star, revealing regions rich in ice and organic compounds that are crucial for planet formation. The results suggest that young planets incorporate these organic molecules in ice during their formation, which may later contribute to a habitable environment. Understanding the chemical composition of protoplanetary disks expands our knowledge of how planets form and evolve. The presence of organic molecules and other complex compounds provide the necessary ingredients for life and suggests that the potential for life is embedded in the very process of planet formation. As these molecules are incorporated into evolving planets, they may be preserved in comets and asteroids, which can deliver them to the planet's surfaces through collisions. Chemical processes in disk are also indicative of dynamic interactions between the forming planets and their environment. For example, the movement and mixing of materials within the disk can lead to the formation of different planetary compositions and atmospheres. This chemical diversity is crucial for the creation of different planetary environments, some of which may also be favorable for the development of life. One of the James Webb Space Telescope's most remarkable discoveries last year was the detection of diamond-like carbon dust from some of the earliest stars in the universe. This unusual finding provides new insights into the processes that shape the early cosmos. JWST infrared sensors can detect the faintest signals from distant celestial objects. Analyzing the spectra of light emitted by ancient stars, scientists have identified signs of diamond-like carbon dust. This form of carbon is characterized by crystalline structures somewhat resembling terrestrial diamonds. Carbon dust plays a critical role in the formation of stars and planets. In the early stages of star formation, carbon dust acts as a coolant, helping the gas inside the molecular cloud to thicken and collapse under gravity. This cooling is necessary for the cloud to collapse and form new stars. As stars evolve and complete their life cycles, they eject carbon-rich materials into space, seeding the interstellar medium with the ingredients needed for the next generation of stars and planets. In addition to cooling, carbon dust contributes to the formation of solids and protoplanetary disks. These disks, composed of gas and dust surrounding young stars, are the birthplaces of planets. Carbon dust in such disks can stick together and grow to form the building blocks of rocky planets. The presence of diamond-like carbon dust suggests that even the earliest planetary systems may have had the necessary materials to form planets. The implications of this discovery extend to our understanding of the early universe. The discovery of diamond-like carbon dust in early stars indicates that carbon was abundant even in the infancy of the universe. This finding suggests that conditions for the formation of carbon-based molecules and potentially life existed much earlier than previously thought. Moreover, the presence of carbon dust in the early universe helps astronomers put together a timeline of cosmic evolution. It indicates that the first stars, known as population 3 stars, which formed shortly after the Big Bang, played an important role in enriching the universe with heavy elements such as carbon. As these massive stars lived and died, they ejected their carbon-rich material, contributing to the chemical complexity of the cosmos. Overall, a carbon-rich environment is essential for the development of complex carbon-based life forms. Although other elements and compounds also play an important role, it's the unique properties of carbon that make it indispensable for the development of life. And it is indispensable, of course, because of its unique ability to form stable, complex molecules. It can combine with 4 other atoms at the same time, creating a huge number of organic compounds essential for biological processes. This versatility allows the formation of long chains and rings that are the basis of proteins and other essential molecules, providing the complexity necessary for organisms to function. Even more intriguing and revolutionary is another discovery made with JWST in June of this year. A team of more than 40 scientists from around the world was able to peer into the protoplanetary disk around small stars. The study of ISO Chi 147, a young star in the Chameleon 1 star-forming region, found the richest menu of hydrocarbons ever observed in a planet-forming disk. Among them is the first detection of ethane outside of our solar system. The discovery of ethane is revolutionary because it is a key hydrocarbon that plays an important role in the chemistry of life. Ethane is a simple molecule that can act as a precursor to more complex organic compounds. These results suggest that protoplanetary disks around tiny stars are particularly effective at forming small, Earth-like planets rather than large gas giants like Jupiter. This is important because low-mass stars are more common in the Milky Way, indicating that there may be more terrestrial planets in our galaxy than previously thought. The protoplanetary disk around this star is characterized by a carbon-rich chemical composition with 13 carbon-containing molecules, including ethane and benzene, but a low content of oxygen-containing molecules, such as water and carbon dioxide. This chemical composition is quite different from disks around the stars like the Sun, where oxygen-containing molecules predominate. The presence of these hydrocarbons in such quantities suggests that the material is transported along the disk in a radial direction, affecting the basic composition of the planets that form in it. These differences in chemical composition mean that rocky planets around tiny stars may have different atmospheres than Earth. For example, the primary atmospheres of many of these planets may be dominated by hydrocarbon compounds rather than oxygen-rich gases. This could lead to the formation of carbon-rich planets with atmospheres quite unlike our own. The discovery of such carbon-rich environments is crucial to understanding the possibility of life. On Earth, carbon is the basis of organic chemistry, underpinning DNA, proteins, and other vital molecules. The presence of similar molecules in protoplanetary disks suggests that the building blocks of life may be widespread in the universe, forming naturally during the formation of planets. Moreover, these findings emphasize the dynamic nature of protoplanetary disks and the complex processes that lead to the formation of planets. The imbalance of carbon and oxygen in these disks may be the result of enrichment processes, where solid particles are stripped of their carbon content, releasing it as gas. These carbon-deprived particles form planets with a rocky, carbon-poor body but carbon-dominated atmospheres. The distinction between carbon-rich and oxygen-rich disks is crucial to understanding the potential for life on these planets. Carbon-rich disks, which are dominated by hydrocarbons like ethane, may favor life forms based on different biochemical processes than those on Earth. In contrast, oxygen-rich disks, containing molecules like water and carbon dioxide, are more similar to the conditions that led to the emergence of life on our planet. This chemical diversity means that planets forming in these different environments could have significantly different atmospheres and surface conditions, potentially leading to a wide variety of life forms or prebiotic chemistry that we cannot yet imagine. The discovery of rocky, carbon-rich exoplanets around small stars not only expands our understanding of the diversity of planetary systems, but also strengthens hope for the detection of life beyond Earth. Small stars around which such carbon-rich exoplanets may orbit are abundant in our galaxy. They're often more stable than larger stars and provide a constant habitat for billions of years. This stability makes it more likely that life will have enough time to develop and evolve. But carbon is not the only key element. What else is needed for life? In the search for life beyond our solar system, the concept of a habitable zone, often called the Goldilocks zone, is crucial. There are areas around a star where temperature conditions are optimal for liquid water to exist on the surface of a planet. Liquid water is extremely important because it is a key ingredient, being a solvent and thus providing the complex chemistry required for biological processes. Habitable zones depend on the type and size of the star. In smaller, cooler stars, the habitable zone is closer to the star, while in larger, hotter stars, it's farther away. Finding planets in these zones is a key challenge for astronomers searching for potentially habitable worlds. One state-of-the-art instrument to aid in this search is the Habitable Zone Planet Finder. This instrument, located on the Hobby-Eberly Telescope in Texas, is designed to detect exoplanets around low-mass stars. By measuring tiny changes in the star's light caused by the gravitational pull of orbiting planets, HPF is particularly good at finding planets in the habitable zones of these stars, which are often dimmer and colder than our Sun. Using the HPF, astronomers have made significant progress in detecting planets where life could potentially exist. By focusing on the low-mass stars that are most common in our galaxy, the instrument increases the chances of finding habitable planets. The high accuracy allows scientists to detect even small Earth-sized planets that might otherwise go undetected. In this context, a very unexpected and intriguing discovery has emerged that calls into question all existing models of solar system formation, shedding new light on the diversity of planetary systems in the universe. The identification of LHS 3154b an exoplanet that's surprisingly massive for its relatively small host star, suggests there are mechanisms at work in planet formation that we do not yet fully understand. Traditionally, models of planet formation such as core accretion and disk instability dictate that the mass of a star limits the size of planets that can form around it. LHS 3154b, however, does not conform to this rule. Perhaps this planet formed away from its star and migrated inward, or perhaps it was captured from another system. These scenarios shed new light on the formation and evolution of planetary systems. It's particularly remarkable that this exoplanet still retains conditions capable of supporting liquid water. The presence of such a planet suggests that habitable zones may exist in a wider range of conditions than previously thought. However, the presence of such a massive planet in the habitable zone of a small star also has implications for the potential habitability of other planets in the same system. Its gravitational influence can make or break the habitable zone, affecting the climate and geology of all small, potentially habitable planets nearby. This can either stabilize conditions for life or make them more unstable, depending on the characteristics of the system. Interestingly, the unexpected size of the planet brings to mind the evolutionary pathways of planets. It may well represent a stage of planetary evolution that we do not yet fully understand. For example, some gas giants may lose their atmospheres due to intense stellar radiation or gravitational interactions, causing them to shrink in size and mass. This process is known as planetary evaporation or shrinkage. In the context of LHS 3154b, its large mass and unusual orbit suggests that it may be undergoing or has already undergone similar evolutionary processes. The planet may have formed as an even larger gas giant by losing part of its gas envelope or in another part of the stellar system, subsequently migrating under the influence of the host star's dynamic environment. Such discoveries challenge the notion that only Earth-like planets orbiting Sun-like stars can be habitable, and suggest that life can exist in a variety of unexpected environments. As we continue to explore space, the quest to discover and understand exoplanets remains a central focus of astronomical research. Current and future space missions should revolutionize our knowledge of these distant worlds, especially those in habitable zones. One of the key players in this ongoing exploration is the Transiting Exoplanet Survey Satellite. Launched in 2018, TESS is designed to observe the brightest stars near Earth in search of transiting exoplanets. Its mission is to identify thousands of new exoplanets, ranging from Earth-size to gas giants, and provide targets for further study by other telescopes. TESS has already discovered many planets, some of which are in habitable zones of stars, making them prime candidates for detailed study. The European Space Agency's Ariel Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, scheduled for launch in 2029, is expected to study the atmospheres of 1,000 exoplanets. By analyzing the chemical composition and thermal properties of these atmospheres, Ariel will help scientists understand the formation and evolution of planetary systems, as well as the potential habitability of these distant worlds. In addition, proposed future missions such as the Louvois and Habex have the potential to take exoplanet research to new heights. The goal of these missions is to directly image exoplanets that are particularly Earth-like and look for signs of habitability with even potential biosigns. By studying the light reflected from these planets, scientists hope to detect biomarkers such as oxygen and methane in their atmospheres. Many exciting developments are looming on the horizon, and they promise to expand our knowledge and inspire further curiosity about the vast cosmos. As we learn more about these distant worlds, the question remains: are we alone in this vast universe, or is life just waiting to be discovered? By now, we have all become accustomed to the idea that life originated in the ocean. But certain questions still make scientists have fierce arguments with each other. For example, how did life transition from water to dry land? Why would a mass meteorite strike be useful? Is collision with another planet important for the development of life? What did Earth look like throughout the first millions of years of its existence, and what obstacles did it have to face? Some of these questions already have answers, and we will share them with you right now. Life that originated in the water and later made its way to dry land appears as a very plausible theory. After all, the oceans currently cover more than 70% of the Earth and contain many different organisms, some of them studied so little that scientists still continue to discover new species. Once on land, these life forms successfully adapted and evolved to eventually become human. Everyone remembers Darwin's theory, where a fish suddenly decided to spend its vacation on dry land. The modern scientists explained this theory. Fun fact: no matter how many refutations of Darwin's theory you read, scientists take this theory as a starting point just as often. The main question is, what is required for a life to form except for the ocean? To answer this question, we must travel to the distant past of the solar system. The process of creation of the solar system is similar to our neighboring star systems. At some point, about 13.6 billion years ago, the Big Bang happened. According to scientists, it was responsible for creating the universe as we see it in telescopes. And the consequences of this event led to the first chemical elements forming. Hydrogen, which compressed and heated under the pressure of the energy from the explosion and turned into a new element, helium. We refer to this bunch of compressed hydrogen which turns into helium as a protostar. But the protostars did not stay with us for long. The main benefit of their existence is the emergence of new chemical elements, which became the building blocks for the origin of life. First and foremost, it led to the emergence of ordinary stars. Every star has a life cycle throughout which the star is akin to a factory. Something is burning, there is some smoke, and streams of resources are flowing through to produce something. Simultaneously, all of these processes affect the ecology and environment. So our sun, like any other star, does the same thing, but on a cosmic scale. And then the life of a star factory is pretty prosaic. It either expands to a supernova or transforms into a red giant or a dark dwarf, followed by attenuation and death. Alternatively, a star can turn into a black hole. We know for sure that the sun will become a red giant, eventually expanding to encompass nearby planets, including us. However, we still have 5.5 billion years before that happens, so we'll have enough time to finish watching our favorite TV shows. What is so special about our solar system? Scientists theorize that the sun was created by a supernova being destroyed not far from the future solar system. Thus, our star, having arisen from compressed clouds of gases, will have eventually absorbed such a high amount of matter due to gravity that it will be enough not only for its existence, but also for the creation of the entire solar system. Everything that was not a part of the new star began to revolve around it, flattening and acquiring the shape of a disk. That's a huge amount of matter. Some of it will be lucky to become a planet, and some will leave the sun's immediate orbit to become a comet or a dwarf planet. The future cradle of humankind came to existence somewhere around here. At the start of its life, Earth was something like a stew of lava, rocks in a liquid form, and crazy mixtures of gases released during the melting process. Near Earth's surface, the temperature exceeded 1,200 degrees. There was no air, only carbon dioxide, nitrogen, and steam. Moreover, the planet was being continuously bombarded by comets and meteorites, some attracted by the planet itself and some attracted by the sun. This is where the water particles that eventually land on Earth come from. But at this point, there is no talk of any life. Earth receives the most powerful blow in its history, but also the most useful, as it turned out later. A planet the size of Mars, which was later named Theia by the scientist, crashes into us. The result of this collision is the formation of the current shape and size of Earth. But even more importantly, the fragments form into our satellite, the Moon. Initially, it was much closer to us, 13.6 thousand miles. This will have an effect later on. The importance of the Moon will become more evident as Earth cools down. Over time, Earth's temperature began to lower, which led to Earth's crust forming, a thick layer of everything that our planet collected due to gravity as it was forming. And after the cooling process, only the very core of the planet, molten iron, remained hot and liquid. It is the activity within the core that creates the magnetic field around Earth and keeps it at its stable moving pace, both around its own axis and around the Sun. As the temperature kept dropping, the planet experienced its first rainfall. Around 3.8 billion years ago, it was subjected to a meteor shower, the remnants from the formation of the solar system bombarding Earth. But inside these bombs, there was also something useful, namely water. Those are not yet the kind of rains we're used to. At the time, the speed of Earth's rotation was so high that a day only lasted 6 hours. However, thanks to that very useful rain, the first ocean is formed on Earth. Meteor showers lasted 20 million years, so the low water content in each individual meteorite was not a problem. Quantity led to quality. At this stage in Earth's development, scientists had a question: where did water actually come from? There are two theories regarding this. Some believe that all the water was brought to us by meteorites. A second theory suggests that there was already water on Earth. The argument was solved by time and new discoveries. Both theories turned out to be right and wrong at the same time. Studying the soil from the Moon's surface revealed that the then young and active Sun burned everything that could evaporate from the planets, including water and gases. And so the scientists still cannot definitively say whether there is more water of meteoric or terrestrial origin present on Earth. And most likely, they will never be able to answer that question. But the main thing is that the collision of Earth and Theia became a catalyst for the beginning of the cooling process of the planets, and subsequently, the formation of Earth's atmosphere, which would serve to protect it from the Sun. The existence of the atmosphere became the shield that maintains everything needed to create life and doesn't let anything harmful in. How did the atmosphere form? Earth has cooled down, but the volcanoes are still active. Due to this volcanic activity, water evaporates, turning into clouds, which then turn into rain. For millions of years, rains fall to Earth's surface, pooling into lakes, then seas and oceans. And this worldwide ocean was very stormy. You know how the Moon influenced the tide. At the time, the Moon was much closer, and its rotation around Earth caused such powerful ocean storms we could hardly imagine the scale. Some waves reached no less than 1,000 feet in height. Meanwhile, the winds on Earth were nearly as fast as the speed of sound. And so the ocean is raging, the storm is at full swing. Where is life? Contemporary theories generally agree on one thing. Back then, Earth's oceans were an ideal place for the emergence of life. But there are several problems. The main question is, how did organic matter, that is, chemical elements that are the building blocks of life, come to exist under these conditions? Let's break it down. Water in Earth's atmosphere at the time, specifically nitrogen, hydrogen, and carbon dioxide, are elements from the inanimate part of the chemical element, so-called inorganic chemical elements. To answer this, let's look at the theory that was developed by Oparin, an academic from the USSR in 1924, as well as a similar theory put forward by a biochemist from the UK named Haldane in 1938. In essence, these theories are simple. The ocean of that time was constantly replenished with organic substances from the atmosphere, which was constantly struck by lightning thanks to the endless storm of that period. It was under the influence of these electrical charges that these elements in the atmosphere turned from inanimate, inorganic, into living, organic, and fell into the water. Once they were in the water, the particles slowly gathered together and formed a broth of organic matter, which would subsequently develop into living organisms. The way these particles behave was similar to the behavior of cells. They can grow, divide, and absorb other chemical elements. But the truth is, the organic matter only acts as the building blocks of the body. Creating life itself requires a team of workers and a foreman to bring everything together. The foreman of our cells is our DNA, an entire library of how everything works, from reproduction to building complex structures from sets of cells. The workers performing the task are RNA. The Oparin-Haldane theory is similar to the story about Frankenstein's monster, whose inanimate matter was also brought to life by a lightning strike. The main thing that we know is that life arose somewhere in the ocean and for 300 million years existed in the form of single-celled organisms. They were not particularly in a hurry to turn into people, were they? But to be frank, the conditions of the ancient Earth would not have given something more complex a chance to develop. The single-celled organisms that existed then were procaryotes. The main difference between them and us is that their organism consisted of one cell without a protective membrane, and in most cases without a nucleus. A good example of the currently existing prokaryotes is bacteria. On Earth, first, oxygen came to exist in sufficient quantities to begin to form the atmosphere in which we now live. And then, within a billion years, somewhere between 3.5 and 2.5 billion years ago, a new miracle took place. Single-celled organisms, even in such a literally toxic atmosphere, have learned to use the energy of light to convert water, carbon dioxide, and solar energy into their first food, glucose. The byproduct of the process produced even more oxygen. We refer to this miracle as photosynthesis. After the cooling of the Earth and the formation of the ocean, a terrible thing happened. 2 ice ages took place. The first, known as the Pongola glaciation, lasted 500 million years. The second, the Huronian Ice Age, was slightly shorter, but it almost exterminated life on Earth. The Huron glaciation lasted 300 million years. It was caused by an oxygen catastrophe. It happened due to the fact that thanks to photosynthesis, unicellular organisms began to release so much oxygen that it led to the extinction of all unicellular organisms that existed without oxygen. And so aerobic organisms, the organisms that need oxygen to exist, became dominant life forms on the planet. Next, prokaryotes continued to evolve into eukaryotes, both our closest and the most ancient ancestors in terms of cell structure. Eukaryotes were able to compete, absorb, and destroy their own kind. They used solar energy as the main source of life and were also able to reproduce. Eukaryotes gradually moved closer to dry land, formed by volcanic activity, producing more and more oxygen along the way. In the shallow water, they united to form the prototype of underwater trees, stromatolites. First, they became red algae, with their key feature being the ability to reproduce sexually. This skill will give an impetus to evolution, resulting in the next prototype of modern nature, mushrooms that grow on land. 540 million years ago, the Cambrian explosion occurred, characterized by the dramatic increase in the number of living organisms. This event prompted the emergence of future animals, plankton, and calcimicrobes. 70 to 80 million years later, another rapid leap in evolution takes place when most of the species known to us today come to existence. The first animals to set foot on dry land were arthropods. At first, they simply roamed the land in search of more satiating food than algae and plankton, but then they never went back into the water. According to scientists, one of the most interesting species that transitioned from life in water to life on land is the tiktaalik fish, Its limbs were like paws, which made it possible for them to move out of the water. For 360 million years, plants, having learned to reproduce by seeds, spread across the land and more. The insects will soon fly into the air. Amphibians, having evolved into four-legged tetrapods, remain on dry land, having learned to hide their eggs from predators and eat a variety of foods. In the future, these animals branch out into several species, giving rise to lizards, birds, artiodactyls, and primates. Yet another blow awaited them: the Permian extinction, which killed 90% of water-dwelling species but left many species alive on dry land. It took the ecology about 90 million years to recover. Then there was the era of the dinosaurs that went extinct due to a meteorite impact, but the birds and half of the other species survived. Life has finally conquered the land. Let's sum it up. Earth has a unique combination of factors contributing to the origin of life. The question about the origin of life remains unanswered, but we have some intriguing clues. Water and the world's oceans are the main source of these answers, but not the only source. Our oceans are unique. They are a result of Earth's planetary evolution. We live in a beautiful time when discoveries related to the transformation of inanimate elements into the living matter are closer than ever. We even envy ourselves a little. After all, the secret of life may soon be revealed.